Hi guys, welcome back to Programming Knowledge. This is Tanit Singhania, and today I will be talking about neural networks, specifically about multi-layer perceptron. A typical multi-layer network consists of an input, hidden, and an output layer, each fully connected to the next with activation function feeding forward. So, forward pass calculates the output corresponding to the inputs. For each training data we give in the input layer, it calculates a score for each neuron. Then the score is given to the activation function. After that, from which we get the output value for each neuron. So this output for every neuron acts in the hidden layer acts as the input to the next layer. So again, a score will be calculated, and then that score will be passed to the activation function. For example, ReLU function or a sigmoid function, and so on. And we will get an output accordingly. So from the output in a training phase, we have the actual and the predicted, from which we can get the loss at the error at the output layer. That error is propagated back to each neuron by adjusting the weights so that we can reduce the loss as much as possible, and that happens in our backward pass. So backward pass is propagates the error backwards through the network starting at the output units. So we have two parts here. First is forward propagation formula and the backprop formulas. So in forward propagation, we first calculate a score, the weight matrix into a input matrix plus bias, as we have seen in the perceptron, and then we have the activated value, that is we pass through pass the score through a function, or for example ReLU function or a sigmoid function. From that value is our output value for that neuron. In backward propagation, for example sigmoid function, we have these formulas in case of in the backward propagation. So we update the weights from ith node to the jth node by n is the learning rate into delta j into output of ith node. So delta j is calculated by these two formulas. If it is an output unit, it is calculated with this formula where tj is your target value, and if it is a hidden unit, then we can calculate by this formula. Okay, so the algorithm is we will begin an epoch, and for each training example D, okay, we have to propagate the network input through the network and calculate the network's output for D's input values. So we will get the output for the training example D. Then from in the is it this is in training phase, so we will get the error from the predicted and the actual value, and we will propagate the error backward through the network. So for each network output unit, it will use this formula, and for every hidden unit, it will use this formula. And then from the delta j, we can get delta wij with the learning rate. So that is added to our old weight. So we will get new weights from ith node to jth node, and then we will repeat it until and unless we get our optimized neural network. Okay, so let us look at an example. Assuming that the neurons have a sigmoid activation function, perform a forward pass and a backward pass on the network, assume the actual output is of y is 1 and the learning rate is 0.9. Okay, so we have given the n value, okay, and we have given the input 1 0 and 1, 3 parameters, and the actual output is 1. Okay, so we have initialized with these weights. These are random values. No, okay, and these are the biases, theta 4 and theta 5, theta 6. Okay, so first we will calculate for h4. For h4 we will multiply the x1 by w14, x2 by w24 and x3 by w34, and sum them up and add the bias to it. Okay, after calculating we get the value minus 0.7. You can calculate it on your own. Okay, then we pass this value to the sigmoid function, as we have given the sigmoid as the activation function for every node. So we get the value as 0.332. Okay, for h5 we again do the same procedure. We multiply x1 by w15, x2 by w25, x3 by w35, and sum them up and add theta 5 to it. So we get 0.1 as the value, and when we pass it to the sigmoid function we get 0.525. Okay, so we have got 0.525 here and 0.332 here. Okay, so when we pass these two values which we previously calculated with the associated weights, we can get the output for sixth output node, that is minus 0.105, and then we can pass this value to our sigmoid function, and we will get a 0.474 as the value. Now since this is an output value, we can calculate the error we got. So since the actual output is 1 and we got 0.474, the error would be 1 minus 0.0474, that is 0.526. Okay, now this, from this error we can calculate our delta 6 for sixth node, that is then output unit. Okay, for the hidden units we can use this the formula previously shown. Okay, so we get the delta 6, 5 and 4. These three are the nodes which we need the delta for. After that we can calculate our delta w. Say for example 4 to 6, we will calculate by learning rate into delta 6 into y4. So we have given the 0.9 as the learning rate, and delta 6 we have calculated over here 0.1311, and y4 we have 0.332. Okay, so we can get the delta value. Then from we will add this delta value to the previous old value, and we will get our updated delta, updated w from fourth node to the sixth node. Okay, similarly we can do for 1 to 4 and every other node in the network. Okay, then after we can update the theta to the biases for which we have the output as 1 only, so we consider it as 1, so we will ignore that term. So the formula would be the learning rate into the delta 6 if it is for the sixth node. Okay, so we will update the biases and our weights. So it would look like something like this. Say for 1 4, okay, a 0.192, it was previously 0.2. Okay, as you can see. So the weights have been updated. You can calculate it on your own. After that, let us perform a forward pass again and see what happens. So like I have shown you previously, we will calculate it and we get these output. Okay, so we will get at the sixth node, we will get the value as 0.061. After passing it to the sigmoid function, we will get the value as 0.515. So previously we got the value as 0.474. So it is improved. It is improved, and the error is 0.485. Previously it was 5 to 6. So error is reduced. So this is only one epoch and only a single training data set. So the values are not improving as expected. If we have more training samples, more epochs, it will reduce, and our neural network would be optimized. In the next video, I would explain you, basically show you how to implement this on a, we will code the complete neural network using our PyTorch library. Okay, thank you.